Good morning to Miss Sam and all my classmates. Today, our group will present about Experiment 5, Friction Force, and Experiment 6, Hooke's Law. Our group consists of 4 people, which is me, Saidah Mayamin, Nur Syafika, Melissa, and Arief. Now, let's start our presentation for Experiment 5, which is Friction Force. Nur Syafika will explain the objectives of this experiment.
So now I will explain about the objective of this experiment. First, to prove the relationship between total force and acceleration on a non-friction surface. Second, to prove the relationship between total force and acceleration on a friction surface. Third, to prove the relevance of Newton's second law of motion. And lastly, to determine the coefficient of kinetic friction.
Now, let's look at the theory behind this experiment. Based on Newton's second law, the relationship between force, mass, and accelerations is given by the equations F equals to ma. This means that a larger force produces greater accelerations, while a larger mass requires more force to achieve the same accelerations. For an object moving on a rough surface, friction opposes its motion. Therefore, the net force acting on the object is the applied force minus the frictional force, which is written as F net equals to F minus F fric. The kinetic frictional force is calculated using F fric equal to mu n, where mu is the coefficient of kinetic friction and n is the normal force. Because the surface is horizontal, the normal force is equal to the object weight, or n equals to mg. These equations form the theoretical basis for determining the coefficients of kinetic frictions in this experiment.
Now I will explain the procedure for non-friction. First, force graph tab will proceed, then the parameter setting will set as object small cred, frictions is no frictions, accelerations of the graph were added by clicking on Add Accelerations button. Force applied were set to 500 N for the first data. Button play were pressed to begin. The accelerations A were recorded and the result were in table 1. Then reset all button will click for the second reading. All the steps above were repeat at least 3 times for each data. As for the friction force, the procedure is the force graph tab will proceed. The parameter settings were set as object small created, frictions would, accelerations were added by clicking on the accelerations button. Applied were set to 500 N for the first data. The button play were pressed to begin. The accelerations A were recorded and the result were filled in the table 2.2. The reset all were clicked for the second reading. The above step was repeated at least 3 times for each data. Step 2 until 7 will repeat for another 9 data.
Now, let's move on to the data analysis. From the table 2.1, as for the non-friction surface, it shows that the acceleration increased linearly as the applied force increased. The applied force shows equally same with the total force of the object because there is no frictional force acting upon the motion. This aligns with the Newton's second law, which states that acceleration is directly proportional to the resultant force when mass remains constant. Meanwhile, for the table 2.2, as for the friction force, it shows that a constant frictional force of 490 Newton acted opposite to the direction of motion. This caused the total force acting on the object was reduced. Although the acceleration still increased as the applied force increasing, the acceleration values were lower than the non-friction surface. This shows that kinetic friction affects the reduction of resultant force and acceleration. Now, let us take a look for the graph. From graph for non-friction surface and friction surface, both show a straight line, indicating the total force is directly proportional to the acceleration. As for the gradient, both graphs initiate the value of 100 kg, indicating that the object's mass remained constant throughout this experiment. The value of the coefficient kinetic friction, which was on question 5, was found to be approximately 0.50, which is slightly different from the estimated value, which is 0.3, that were stated in the laboratory manual. This may be caused by experimental error, such as sensor calibration error, slight variation in the roughness of the wooden surface, friction in the pulley system, or human error during data collection.
In conclusion, the experiment successfully demonstrated Newton's second law of motion. The results show that acceleration is directly proportional to the total force when the objective mass is constant. On the wooden surface, kinetic friction reduced the resultant force and the acceleration were also reduced. The gradient of both graphs shows an object mass of 100 kg. The coefficient of kinetic friction calculated from the experimental data was 0.50, which is slightly different from the theoretical value 0.30 due to the experimental error.
Now, let's proceed to experiment 6, which is the Hooke's law experiment. The objective of these experiments are, first, to investigate the relationship between the applied force and the extensions of a spring. Second, to verify Hooke's law by determining whether the extension is directly proportional to the applied force within the elastic limits. The third one is to determine the spring constant from the gradient of the force extension graph. And lastly, to prove that the work done in stretching the spring is equal to the elastic potential energy stored in the spring.
Next is the theory. Our experiment relies on Hooke's law, which states that a spring's extension is directly proportional to the force applied to it, as long as it stays with its elastic limit. Beyond this limit, permanent deformations occurs. On the left, the formula F equals to negative kx defines this relationship, where k is the spring constant and x is the extension's distance. When force is applied, mechanical work is done on the spring and stored as elastic potential energy. This work done is equivalent to the area under a force extension's graph, represented by W equals to 1/2 Fx. Ultimately, this concludes that the total elastic potential energy stored in the system is expressed as E equals to 1/2 power of 2. Ngam ka? Ay, not record. Ay, Baisan.
So now, let's look at the procedure. First, the mass of wooden block is measured and recorded as M. Second, the apparatus were set up based on figure 5.2 in the laboratory manual. Third, the tabletop were made sure are stable and horizontal to the ground. Fourth, the spring scale and the wooden block were attached with a string. it were placed horizontally on the tabletop. The rubber side of the block is made sure to be faced downward. Next, a M equal to 50 gram mass were placed on the wooden block. And next, the spring were pulled slowly. Once the block started to move, the spring scales reading were recorded. The value were recorded as Fx and filled in the table 5.1. Next, step 4 until 5 were repeated for 3 trials. Another 50 gram mass were added on the wooden block, and step 5 to 6 were repeated. The steps were repeated until total of M equal to 500 gram mass on the wooden block. Step 1 until 8 were repeated and the rubber side of the block were made sure to be facing upward. The data obtained were filled in table 5.2.
Now let's move on to the data analysis. From the table 5.1 shows the relationship between the applied force and the extension of the spring. As the applied force increases, the extension of force also increases. This proves that when a smaller force is applied, the extension of the spring also gets smaller. Meanwhile, increasing the applied force produces greater extension. This indicates that the spring stretches proportionally with the increasing load. The data also shows that the extension increased at a constant rate when the force increased. This indicates that the spring remained within its elastic limit during the experiment. This indicates that the spring returned to its original length after the load was removed and did not deformation. This data confirm the Hooke's law, which states that the extension force of spring is directly proportional to the applied force and the elastic limit is not exceeded. As for the graph, based on the graph, it shows that they're slightly curved rather than expected a straight line. This may be caused by the parallax error when reading the meter rule, slight oscillation of the spring when measurements were taken, or the inaccuracy of measuring the extension. The spring constant on question 1 was calculated from the gradient of the force extension graph and was approximately 49.15 Newton. The spring constant K represents the stiffness of the spring, where larger value indicate a stiffer spring that requires bigger force to produce an equal extension. This indicates that the spring remained within its elastic limit. Since the graph was slightly linear, it somehow proves that the spring obeys the Hooke's law. For the work done calculation, it is calculated using the formula work done equals to 1 over 2 Fx, where Fx is equal to force proportional to the direction of the displacement. The value of the work done is equal to 0.92 joule. Since work done is equal to elastic potential energy stored, the elastic potential energy was also calculated using elastic potential energy equal to 1 over 2 kx squared, which gave the same value of 0.92 joule. The equalities between the work done and the elastic potential energy proves the principle of conservation of energy. This also proves that the work supply is fully converted into elastic potential energy because negligible energy was lost to other factors such as heat and sound. This strongly proves that the calculation was correct and the spring behaved as an ideal elastic spring.
In conclusion, the experiment successfully demonstrated Hooke's law by proving that the extension of a spring is directly proportional to the applied force. The spring behaved as an ideal elastic spring because the spring constant remained constant within its elastic limits. The linear force extension graph also supported this relationship. The gradient of the graph gave a spring constant value of 46.15 Newton per meter, indicating the stiffness of the spring. Furthermore, the value of work done and elastic potential energy were both calculated to be 0.92 joule, proving that the work done in stretching the spring was stored as elastic potential energy. Overall, the objective of this experiment was successfully achieved despite minor experimental errors.
Thank you for your attention. That's all from our group. I hope by these presentations you all get a better understand about the applications Newton's second law and Hooke's law.